subscripted variables or arrays. Till now we have worked on variables. We can store a value in a variable, but sometimes we need a facility that can store more than one values so that the programming logic becomes simpler. So to store more than one values in one variable, we use subscripted variable. A subscripted variable has variable name and a subscript. We make extensive use of subscripted variables in algebraic equations. Subscripted variables are capable of handling more than one values. Here we know that xi is a subscripted variable. So xi refers to ith value of x. Likewise, x3 refers to third value of x. We can also use variables to represent subscript. For example, if I is 2 and j is 4, then x I plus j minus 1 will refer to fifth value of x. A subscripted variable can have one or more subscripts. A subscripted variable with one subscript is called as a single dimensional array. Similarly, a subscripted variable with two subscripts is called as a two-dimensional array. So let us study how subscripts are used using a demonstrative example. So this example shows how we can use subscripted variables. There are some statements we are not familiar with, but we will study these statements afterwards. So A3 refers to third value of A. We have stored 1.2 at A3. Likewise, we have stored 4.5 at A5. We have set k to 10, and ak minus 2 refers to A8. So value of k, that is 10, has been stored at ak minus 2, that is A8. So A8 is equal to 10, A5 is 4.5, and A3 is 1.2. We have not set other values. That simply means those values are undefined or garbage values. To see what advantage subscripted variables offer, we can see that I can display all the values of subscripted variable A by using a do loop. Here I have written subscript as I, and value of I varies from 1 to 10. That simply means I will display all values of A using this do statement. So let's execute the program. You can see that it has displayed 10 values. We have defined only few values, that is value of A3, A5 and A8. So only those values have been defined, all other values are undefined. You can see that there is a dimension statement. This dimension statement is a statement which is used for allocating memory space for subscripted variable. This step is required because a subscripted variable can store more than one values. This is not required for plain variables because those variables need only one memory location, and that is known to computer. Whereas in this case, the actual space requirement varies depending on the size of the array. The space allocated here is the maximum allowable space required. Actual space used may be less than this or equal to this. Let us go back to presentation and continue with the presentation. So there are different types of arrays depending upon how many subscripts those arrays have. A one-dimensional array is like a list of values or a row matrix or a column matrix. A one-dimensional array has only one subscript. A two-dimensional array is like a rectangular matrix or a table of values. The first subscript is assumed to represent a row number, and then second subscript refers to column number. For example, x31, here 3 is the row number and 1 is the column number. A three-dimensional array may be treated as a set of rectangular matrices or a set of tables. The first, second and third subscript represent table number, row number and column number. For example, X413 may be assumed to refer to first row, third column and fourth table. First row, third column of fourth table. FORTRAN uses subscripted variables as follows. A subscript must be in the form of an integer expression. Subscripts are written after the variable name, enclosed in parentheses, separated by commas. We have seen how a subscripted variable is written, but we have seen only a single dimensional subscripted variable. Let us learn how a two-dimensional subscripted variable works. Let us consider a two-dimensional array of size 4 by 3. So this array has been shown in the form of a table here. So there are 4 rows and 3 columns. Following statements, when executed, will have effect on the array. There are some statements. These statements will have effect depending on what is written here. So we can study this effect using this example. X13 refers to first row, third column of X. So that is first row and third column. So this location. So here we have stored 4.7. So we can see this value is actually erased, but we'll see why this has happened afterwards. So 4.7 is stored at memory location 13. Stores 4.7 in or at location x13. x5 minus 3, that is x2 comma 1, gets 5.2. So stores 5.2 at x21. 1 gets 5.2. Likewise x12 2 gets 7.2. I is 2 and j is 3. So ij refers to 23. So x23 gets 5. x23 gets 5. xji, that is x32 gets 9.5. x13 gets value of x21. So x13, that is this memory location, gets value of x21. So x21 is 5.2. So this value will be stored here, but because there is already a value, that value will be erased. That value has been shown erased like this, and new value will be stored, and this will store 7.5 at location xii, as I is equal to 2. x22 gets 7.5, so x22 gets 7.5. So this is how we can work on arrays. So arrays through their subscripts provide a very convenient mechanism for working on multiple elements. That is what we have seen earlier. So let us study a program module. This program module demonstrates how we can use arrays. So there are two loops. The outer loop varies from 1 to m, and the inner loop varies from 1 to m. Let us assume that we are working on a square matrix of size m by m. The statement inside says if I is equal to j, then xij is equal to 1. That means when both the subscripts are equal, then x gets value 1 and otherwise it gets value 0. So this is the module which can generate a unit matrix. So in case of unit matrix, we know that all diagonal elements are 1. That means a diagonal element is a element which has row number and column number same. So diagonal elements get 1 and other elements get 0. So this way we can generate a unit matrix without assigning values to each individual element separately. We can either use this module, or we can write a slightly compact module using this technique. Here we have written a loop. I varies from 1 to m, j varies from 1 to m, and xij is assigned value 0. So all elements are initially assigned value 0, and After that, we assign value 1 to xii. So that is two diagonal elements. So it will erase this value and then it will store 1 at the diagonal location. So this way we can work on subscripted variables using program logic. So working on arrays is very simple because of this facility. The subscripts can be manipulated programmatically, and that allows us to write many uh, modules which are very compact in nature. We have seen earlier that there is a dimension statement, and we have seen that the dimension statement is used for allocating memory space. So the statement is used for specifying size of array used in the program unit. This statement is a non-executable statement which must appear at the top of the program module before first executable statement. We have seen that the statement was written at the top of the program. The syntax of dimension statement is like this. Dimension, this is the keyword, followed by variable name, followed by size of variable, the first variable, then second variable, followed by size of second variable, third variable, followed by size of third variable, and so on. So here var1, var2, etc. are subscripted variables being declared, and size1, size2 are the sizes of variables var1, var2 respectively. Dimension statement is used for allocating memory space for subscripted variables or arrays. The actual array size used can be smaller than or equal to the allocated space. So this space allocated is the maximum space allocated. The actual space used may be smaller than this, or it can be equal to this, but it cannot be greater than this. The size of subscripted variable is in the form of an expression. There can be one value or there can be more than one values, but it has to be a constant expression. So depending on type of subscripted variable, we can write one or more values. In case of two-dimensional subscripted variable, there will be two values separated by comma. In case of three-dimensional subscripted variables, there will be three values. The size of an array may be expressed in the following two forms. So there are two ways in which we can declare array using dimension statement. Study form 1 here. In this case, the size is specified in the form of list of non-zero positive integer constants separated by commas. The form specifies maximum possible value of a subscript. The first subscript in this case is always equal to 1. So if you specify dimension using this form, then the first subscript will always be equal to 1 and the last subscript will be the number indicated in the dimension statement. For example, x50 refers to a single dimensional subscripted variable with first subscript 1, last subscript equal to 50. So it will have 50 elements, x1 to x50. Likewise, here y has maximum 7 rows and maximum 5 columns. So row number 1 to 7 and column number 1 to 5. Likewise, p has 4 elements, p1 to p4, and z has n element. We have seen that the size has to be in the form of a constant expression. So here we have declared n as a constant with value 50. So this refers to z50. So z will have 50 elements starting from z1 to z50. The dimension statement given above declares x as one-dimensional array with 50 elements. We have seen that. Y is a two-dimensional array, that is a rectangular matrix with 7 rows and 5 columns. P has 4 elements and Z has 50 elements. So we have seen this. The second form is slightly different. In this case, the size is specified in the form of a list of ranges. It is written in the form n1 to n2, and this range is separated by commas. This form specifies both the first subscript and the last subscript. not the first and last subscript, first value of subscript and last value of subscript. So n1 and n2 must be valid integer constant expressions. For example, if we write dimension like this, dimension x 5 colon 50, this means that the first value of x is x5 and the last value of x is x50. Here the first row of y will be y minus 3 and the last row of y will be y7. Likewise, first column of y will be 5, that is y5, not y5. It will be first column of y will be 5 and last column of y will be 10. So remember, first row of y will be minus 3, last row of y will be 7, first column of y is 5 and last column of y is 10. Here P is a single dimensional array. First element will be P4 and last element will be P9. You can also use type declaration statement to declare arrays. We have seen how to use dimension statement. Now we'll see how to use a type declaration statement to declare array. Here we can see that m is a real variable, so it has been declared this way. So we have first declared m as real variable and then we have specified dimension. So dimension m100 means that x will have 100 values, m1 to m100, and the variable m will be a real variable. So these two steps can be combined in one step this way: real m100. So this statement is equivalent to these two statements. So this form is more convenient, and therefore we can use this. The second alternative is more convenient, that is what we have seen. So let us refer to some program examples. So this program demonstrates how we can use array. So there is a dimension statement. It declares array t. Size of array t is 31. So it reads value of variable n days, number of days. This program assumes that we are reading temperature data for number of days. So from a value of I equal to 1 to n days, this will read values of t. So t will have actual number of elements equal to n days. After that, we have calculated value of x. So from this program you can see that s is sum of all values of t. So s equal to s plus ti. I initially is equal to 1, then it will be 1, 2, 3, 4 and so on up to n days. So we have added all values of t to variable s. We can calculate average temperature AT by using this equation, sum s divided by number of days, and this way we can display average temperature AT. We have also here we are calculating deviation of day's temperature from average temperature. So difference is calculated by using Ti, that is temperature at ith day, minus average temperature. Here we have displayed day number followed by the difference. So this program demonstrates how we can work on subscripted variables. You can also see some other examples. So let us study this program. So this program demonstrates how it is convenient to work on arrays. So there is a dimension statement 18, so that means 10a will have 10 elements. This loop varies from 10 to 1 because the increment is minus 1. So first value of I will be 10, second value 9, 8 and so on up to 1. ai gets value I. So initial value of I is 10, so a10 gets 10, a9 gets 9 and so on. So this way we will store values in each element of I, and after that those values are displayed, but starting from first element to last element. So values are actually stored in reverse order but displayed in the given order. So let's focus on first part only. So the part after this line will be ignored right now. So we'll execute this part and see what happens. So the first part displays numbers from 1 to 10. This has happened because we have stored initially I is 10, so A10 gets 10, then A9 gets 9, and so on. So when it is displayed starting from first to last element, we get 1, 2, 3, 4, 5, and so on as the output. So that is what we have seen there. The next part, we have stored values at alternate location. So I starts from 1, next value of I will be plus 2, that will be 3, 5, and so on. So the odd elements get value 100. So all other elements will be what is assigned here. So we can see that we can assign values to elements using some program logic. So here we have assigned values to odd locations using this loop, and then here we'll display all the elements again. So if you go back to the output, you can see that the odd locations, the odd locations have been assigned value 100. So first location, third location, fifth location, seventh, ninth, and so on. So this way we can see that we can manipulate memory locations using program logic. Let us study this example. This example demonstrates how we can use the alternative form of memory allocation. A 2 colon 5, this represents that matrix A, or this statement says that the matrix A will have rows starting from 2, that is A2 will be the first row, and A5 will be last row, second row to fifth row, and the number of columns will be column number 10 to column number 20. So the first value of A will be A210 and the last value will be A520. To assign some values, we have written this program module. I varies from 2 to 5, J varies from 10 to 20, and we have assigned value 5.5 to each location, and then we have displayed values using implied do loop and do statement combination. We'll study this part afterwards, but let us remember that this part displays complete matrix in matrix form. So here you can see that all elements are 5.5 and the matrix has been displayed. So first row is row number 2, 3, 4, and last row is row number 5. Likewise, first column is column number 10 and last column is column number 20. So this is how this program works. So this is the end of module.